Hello everyone, my name is Joshua Four and I will be presenting the one-dimensional transient heat transfer assignment for Dr. Lawrence's Chemie 3102 class. So the problem that we were assigned for this assignment is a brick wall with thermal diffusivity of 4.72 times 10 to the negative 7 meters squared per second with a thickness of 0.5 meters is initially at a uniform temperature of 300 degrees Kelvin, and we are asked to determine the length of time required for its center temperature to reach 425 Kelvin if its surfaces are raised to and maintained at 425 and 600 Kelvin. Here are some of the essential equations for solving this problem. And here we will start with the transient heat transfer equation, where this first T term is going to be equal to the temperature on the left side of the wall, and this second T term is going to be equal to the temperature on the right side of the wall. And so we can rearrange this equation to solve for the temperature at the center of the wall as a function of time, which is what we are looking for in the question. And then also we know that the stability criteria for a one-dimensional problem is less than or equal to 1/2. And this is important because it allows us to simplify the above equation by eliminating the last term completely. So to better visualize the problem, created this simple diagram of the brick wall, and here you can see that the left side of the wall is raised to and maintained at 425 degrees Kelvin, and the right side of the wall is raised and maintained at 600 degrees Kelvin, with the center of the wall being initially at 300 degrees Kelvin. And here down at the bottom we can see that the wall is 0.5 meters thick, or 0.25 meters to the center of the wall. So here is the initialization of my code, and going down in order we see that A is equal to the alpha value, Ti is equal to the temperature at the center of the wall, T1 is equal to the temperature at the left side of the wall, T1 is equal to the temperature at the left side of the wall, T2 is equal to the temperature on the right side of the wall, dx is the distance to the center of the wall, T is equal to our total time, I is simply an iteration counter, and then T1i is an array that is going to hold all of our T1 values, and T2i is the same for T2. And then Ti is an array which is going to hold all of our time steps, so that we can actually get the final time it takes to reach 425 Kelvin at the center. And Tc is the array that is actually going to hold the temperature at the center of the wall. And these T plus and T minus variables are simply allow us to calculate it in the while loop, which is right here. This is my while loop that I used to solve for the time needed for the center of the wall to reach 425 degrees Kelvin. So in this we can see that we initialize the loop by setting T1 and T2 equal to the initial values, and then we run the loop in the range of 10, we run 10 times, and then here the T1, this is going to get us a new T1 value, and then T2 likewise for T2 using our T plus and minus, and then these T1i, T2i appends is going to add this new temperature to our temperature array, and then these T plus T minuses is going to make a new T plus T minus assigned from the T1 and T2 values. Below this we have the actual calculation, which is just the formula shown in the previous slides. And then down here we get this is the temperature append function, which is going to add our time step into our time array and divide it by 3600 so that our time is in hours. And then the final thing is simply adding our temperature functions to our temperature values to the temperature array. And then finally, this is just simply to print the value of T. So this is a graph I made in Python of the temperature at the center of the wall versus time. And I made this graph using the arrays for temperature and time that I created in Python. And the while loop calculated that the time it would take for the center of the wall to reach 425 Kelvin is 16.46 hours. Finally, we are also asked to determine the stability criteria for 2 and 3-dimensional flow, and we know that the criteria must be lower than the criteria for 1-dimensional flow, and this is to account for more directions of flow, and this led me to find that for 2D the criteria is 1/4, and then for 3D the criteria is equal to 1/6. Right, that's the end of my presentation. Thank you.